All right, so frequency response in Bode. Let me start by quickly give you an idea where we want to go today. So last time we discussed transfer functions. And transfer functions, we understood them as just yet another way to represent ODEs, yet another way to represent systems that we will want to control soon. And it wasn't clear why exactly we wanted them. Well, there are a number of reasons to want transfer functions, but one of the most clean reasons is to do Bode analysis, to do Bode plots. So Bode plots are probably, is there a problem with the screen sharing? You're supposed to be able to see it. If Yaroslav, if you can see the screen, just try to maybe close the messenger or close the. I mean, just work with that. It should work. All right. Sorry for the interruption. Anyway, so one of the most clean reasons is to do Bode analysis. Bode analysis is useful in a way which is not occluded by equivalent methods in different newer tool sets of control theory that we are going to study later. So, for example, stability analysis used to be done in transfer functions, but now we can do it by finding eigenvalues. Finding eigenvalues now is a matter of milliseconds. It can be done on any computer. And although we don't always do it, there are whenever we want to do something about stability, we find the ways which don't involve transfer functions, basically. But Bode plot that we are going to study today doesn't have any better, it doesn't have anything that can replace it yet. There are, advanced techniques that I think probably should, eventually replace it, but it's at this level, of complexity, Bode plot is. So even now is still something that you cannot simply discard and replace by normal algebraic computations like with eigenvalue analysis, for example. So Bode plot is a unique tool, and Bode plot will introduce to us, like transfer functions for us was a way to discuss for the first time how the input relates to the output of the system, how we take in the input, how do we react to it. We didn't do any analysis on that. We just discussed that, here's the input, transfer functions transforms this input into the output, right? Well, Bode plot will be the first tool to analyze how this transformation takes place. And for you, what is important is that with Bode plot, you will be introduced to, one second. With Bode plot, you would introduce to the way of thinking, which you can then, in your self-study or whatever, transfer to many other, areas of control theory. So part of it is just immediate usefulness of Bode plot. Part of it is philosophy that will be helpful for you in your studies overall. All right. Now, let me just jump into the content. So first of all, I will try to somehow motivate it through connection to Fourier transforms. And that is a popular way to do the motivations here. So first of all, you remember Fourier series, right? It represented periodic functions as sum of harmonics, sines and cosines. The coefficients of the series is a discrete spectrum, right? That's what you can think about it. Fourier transform is kind of the same, but it gives you a continuous spectrum of the function. And the basis of this continuous spectrum is same as before, as in Fourier series, is sine and cosine, sines and cosines. So basically, you can think of Fourier transform, same as Fourier series, as a decomposition in terms of sines and cosines. That is what I said in the introduction of the previous lecture, but no, it bears repeating. Now, Laplace transform, as I said again before, it also gives a continuous spectrum, but in a different basis. It is in terms of complex exponentials. You can think about it as solutions to second order ODEs. Oh, sorry. Sorry if I made you are unable to unmute yourself. No, you should be able to unmute yourself. It's just that we always get some stray sounds in the chat, so that's why you have mute upon entry option. Anyway, please remind what spectrum is for a function. Spectrum, how should I put it? I don't think that is something we need to spend time discussing, because that is, again, one of those concepts that would take a while to give proper definition. But don't think about it as a spectrum of a function. Think about it as a spectrum of a signal. You saw, think of music. You saw music as a signal, right? If you opened any editor, video editor, audio editor, you saw music as this, combination of sine waves, basically like a forest of lines. That is the music and time domain, right? Right. So you can imagine, you can represent it as a spectrum, like what frequencies, how should I put it? What frequencies constituted, right? But of course, frequencies. How should I say it? It's when I say spectrum, is what I'm talking about is just trying to decompose it into a finite number of sine waves if it is a discrete spectrum, and the computers always use discrete spectrums. I'm just saying, okay, the recipe for reconstructing the same audio track is to add this number of sine waves with those weight coefficients. That would be spectrum. But just think, if spectrum doesn't ring a bell, if the word doesn't make a lot of sense to you, just drop it. Doesn't matter. We can study it separately. My point with this slide is just to say that Laplace is same as Fourier, but instead of sines, we have exponentials. Complex exponentials. And complex exponentials, let me just quickly remind you what they are. Complex exponentials are, let's say, e to the power minus s. If s is, let's say, something like, what would be a good second letter? I don't know. Let's just write like this. Oh, wait a second, like this. So if this is a complex number, this is a complex exponential, you can write it as something like this, right? And this in turn, using Euler identity, I believe it's called, or whatever, fundamental identity of something. One of those terms, that would be cosine omega plus j sine omega, as far as I remember. So what I'm trying to say is complex exponentials contain a, sorry, minus sign for both, right? Complex exponentials contain the real part and complex part and imaginary part. And real part is just an exponential. Imaginary part is just a periodic function. So Laplace transforms contain both like exponential part and the trigonometric part. All right. Okay. Now let's one more time compare Fourier transform and Laplace transform, just to be sure they are indeed similar. Okay. So here is the Fourier transform. Notice the variable for the Fourier transform. This guy is a real variable, the real number. Notice the variable for Laplace transform is a complex number. However, the kernel of the transform, this guy here, is surprisingly similar. The difference is that this kernel is purely imaginary. Why? Oh, here's imaginary. Here's imaginary 1, and everything else is real. So the whole thing is imaginary. This is a complex number. Can be imaginary, real, can be combination. So the two are different in this aspect. This is purely complex, purely imaginary. Sorry, this is arbitrarily complex.
Excuse me.
Yes.
Sorry to interrupt. Are we denoting the square of -1 by g in this case, right?
Yeah. I will in this lecture I will use g as a.
Okay, thank you.
Thank you for the question. All right, so I hope this is clear, the relation between the two. And remember what I said before, that e to the power s, let's write it as st. We're going to write it like this. It's the same as e to the power minus sigma if s is equal to sigma plus g omega times e to the power minus g omega. Why, this is clear, right? Why addition here leads to multiplication here. This is how powers work, right? I hope this transformation is clear. I think that's something that can easily go over your head if you don't pay attention. So let me just give you like a funny numeric example here. Let's say you have 10 to the power 3, right? That is 1000. Okay, that is the same as saying 10 to the power 2 plus 1, right? That's still 1000. That's the same as 10 to the power 2 times 10 to the power 1. Still 1000, right? Just remember that there is this relation for exponentials for powers. The sum can be transformed into this multiplication. That is a very interesting algebraic property, by the way. There's a lot of interesting math that can be done by observing this stuff. All right, so this is what you can write. So let me even stop here and just notice that if this guy is equal to 1, then they become equivalent. Well, when would this guy be equal to 1?
Sorry, Professor.
Yes.
But where is the t?
Yeah, as I said, this is not going to be my best lecture. Yeah, T is here. Thank you. All right, so when is this guy is going to be equal to 1? Oh, T is arbitrary, right? So when's let me just try to clean it up a little bit. This guy is going to be equal to 1 when basically sigma is equal to 0. Right. I hope we draw enough attention to the fact that Fourier transform is almost the same as the Laplace, except it is more limited. It is purely imaginary kernel, where here it is arbitrary complex kernel. Good. Now, moving on. All right. Now, here, I guess maybe we could have tried to go back to analyzing the. Let me just get a. Do we have a option to share a black whiteboard? Yes, we do. 1 second. Right, let me just write it here. So you remember the solution to a second order ODE. What's the second order ODE? You remember second order ODE is something like this. Something like this. Solution to second order, well, let me just write homogeneous ODE, so 0 here. The solution to it would look like what? It would look like y to the power lambda t, and I think that's it, right? Times initial conditions. Maybe there is something here like a plus. I'm not sure, but I think that's correct.
I think so. It depends on the coefficient mainly, because it can have sinuses, for example.
Yeah,
Cosinuses.
yeah, exactly. But what I've written
is like a special case, particular.
No, it's not special cases. Contains cosines and sines. Well, alpha here is a
complex
eigenvalue. Eigenvalue of the equation, and if it is complex, then indeed this will be if eigenvalue is complex. That's shorthand. It's not a math notation because real is also some part of complex. But you understand what I mean. And the solution, stable solution, for example, would be like this, right? All right. If eigenvalue is purely real, then solution would be stable eigensolution would be something like this, for example. All right. So just a reminder how those solutions look like. All right, but that is all cool and nice, but let us think about the following. Let's imagine a linear equation. I'll write it again. Sine, let's say, omega t. Sorry about horrible handwriting. So anyway, here we have y, equation for y. Here we have sine omega t. So what would be solution? Well, the solution would be solution. Let me try to at least write it somewhat intelligible. Solution y of t would be homogeneous solution, which is what we gave before, plus particular solution, right? And what is the homogeneous solution? Let me write it again. It would be e to the power lambda t, initial conditions here. And what is particular solution? By the way, this is all not to like study. It's just to kind of bring back the image in your mind. So concentrate on the ideas.
Should be a linear combination of cosine and sines of WT.
Particular solution?
Yes.
Particular solution, yeah, it would be indeed linear combination of cosines and sines. So how should we put it? What I'm tempted to say, that I'm not sure how correct I am, but I'm tempted to write it like this. I'm tempted to say it is maybe C1 times E J omega t. I think maybe I'm wrong. But my point is that for sure, particular solution would have the same frequency here. Why? Well, it kind of makes sense that after transient process is over, your sine wave, your solution will have the same frequency as your input. So let's say you have input as a green line, and you have your particular solution, and you have your solution to your equation as a blue line. They have to have the same frequency. That is, I'm giving it to you without proof, but I think that's something you can believe in. They're not going to go at different frequencies. They're going to have the same frequency. Okay, that is a very interesting fact, by the way. Okay, what does it leads us to? Well, what it leads us to is that if we look at this equation here, what we see is it has two parts. This part that contains response to the input, and this part that doesn't. And if we want to analyze how a system responds to an input, we don't need to care about this part. Like, as long as what we care about is how the system responds to the input, we don't need homogeneous solution. That's the key idea. All right, sounds sounds okay. And what we also discard with this part is the transient process. Like here, there is no transient process. There is no, what is a transient process? That is something that goes to zero after a while. And where does it come from? From a real part of the eigenvalue. Real part of the eigenvalue, if it is negative, it represents the exponential. And the complex part of the eigenvalue represents the shape. So it's basically transient process is just this guy. So if we put it to zero, well, it would lead us to the particular solution. Right. So that is kind of like the feeling I want you to have. What we care about here is particular solution, not homogeneous solution. Okay. Let me go back to the screen that I wanted to share. Okay, Now, again, from analyzing solutions to linear DEs, we know that given a harmonic input, after transient process is over, the solution approaches harmonic with the same frequency, but possibly different amplitude and phase. Okay. Intuitively, we can think of the imaginary part of C, this Laplace variable, as having to do with the frequency response. All right, that is the intuition, right? Imaginary part of C has to do with frequency response. Intuition, not math. But with this topic, unfortunately, a lot of what we have to do is find intuitions rather than doing math. That is my personal biggest problem with teaching Laplace transforms. It's a little bit difficult to expect to cover all the math in 2 lectures. Now, the kernel function for the Laplace transform, this guy, as we wrote before, is a complex variable. If we put sigma to 0, the kernel becomes this guy. And what is this putting kernel to 0 or putting sigma to 0? Well, you can think about, again, it in 2 ways. One way is we do it to kind of imitate the time when transient process is over. So the exponential, the part that had to do with exponential decay is already decayed into nothing. Or, it's basically, I guess a better way to say it is just that exponential part doesn't matter, right? Or another way to think about it is just to say, okay, as long as this is true, Laplace transform becomes a Fourier transform, and we are just decomposing our signal into frequencies rather than into exponentials. All right, that is intuition. Again, it's not math, it's intuition. Laplace transform, but with the real part of the again complex value to be 0. Now, what is Bode plot? How is it done? That is, there's something to remember basically. The first idea of the Bode plot is substituting this purely complex variable in place of Laplace variable into the transfer function. So your original transfer function was a function of Laplace variable. You make it a transfer function in terms of this complex variable. You go from Laplace domain to frequency domain, the way we call it. I guess what we could have said was that we, instead of Laplace, we do Fourier transform, but people don't talk about it this way. So people say we went from Laplace domain to frequency domain. And the motivation you commonly hear is that we don't care about the exponential decay part of the process when we discuss frequency response, because as you saw, in particular solutions, there is no exponential decay. It is a transient process feature. Okay, good. Now, given transfer function, we analyze, as I said, we analyze its behavior when this guy is equal to 0. How do we analyze it? Well, what we can do is we can plot its amplitude. Remember, this is just a scalar. And as a complex number, it has like 2 properties basically, right? Like real and imaginary part, or amplitude and phase. So we can plot its amplitude like this, right? And we can plot its phase like this. And we can discuss those. All right. Oh, sounds fun, right? We can do it. It's very, very interesting. Bode plot is very similar, except in the Bode plot, what we plot is 2 things. First is this 20 logarithms of the amplitude of the transfer function. And second is in degrees, the phase. Now, let's just look at it for a second. It looks like suddenly too many symbols, right? Like you look at it, here is vertical lines, here's atan 2, im, real, 20, log, pi, too many symbols, right? But it is actually very simple, yes.
Could you please repeat what is atan 2?
Atan 2 это arctangents, arctangent.
Why 2?
Yeah, that's interesting, right? I wouldn't expect this question. It's kind of interesting because that's how do you find arctangent, right? You call a function usually, right, to compute it. Like what? So let's say I want to find arctangent of a. I would say phi is equal to tan -1 of a. Okay. But you know that this, by itself, this function is not, how should I put it? You know what a tangent is, right? Tangent is
Sinus by cosine.
Yeah, is a sine divided by cosine, right? And there is more than one angle usually that can produce the same tangent. Is that correct? Like on this wheel of from 0 to 180 to 0, there is more than one angle that can produce the same output. Am I right?
Yep.
Yeah, it's true.
Yeah, for example, 0 corresponds to this angle and this angle. Right?
No, it's wrong. We cannot divide by 0.
But it's cosine
Yeah,
1.
yeah. Sine of 0 is wait, no. Here, sine is 0, cosine is 1.
Okay.
Yeah. So you can kind of see that already this function inverse doesn't actually exist in mathematical point of view. Like we cannot define this function because it has two different outputs, even on this 360 wheel. And in programming, in like day-to-day, down-to-earth, student level programming, I'm not talking about anything, in the cosmos, just normal programming that you already probably could experience. This problem exists as well, right? Like even if you develop like a small application or a video game or whatever, you still need to compute angles often enough. And this problem obviously will occur. Like you want to compute angle from coordinates, like let's say, okay, here's a dot, here's a character. You want to know the angle, like, is it in the field of vision or not? You want to see this angle. Sorry, again, today I cannot draw. You want to see this angle. So you want to see if it is in the field of vision. And you won't be able to do it like trying to call inverse of the tangent. Well, because of this problem, right? You would have different. I'm not saying that this is the same tangent, but what I'm saying is you'll find. I think that will be the same tangent actually. You'll find that it has multiple solutions basically, so it just won't work. And but this is not a problem. Like this is not a problem. Why? Oh, because usually you never want to compute a inverse tangent. That is very rare. Because tangent assumes that you have a single input. But usually what you have is two inputs. You have separately sine and separately cosine. You have coordinate x, coordinate y, right? That's what you usually have in practice. And if you have those two coordinates, you can exactly find out one solution. And the function that acts as a tangent, but takes two inputs, x and y, is called arctangent 2. It is the same function as arctangent, but takes 2 inputs. And as taking 2 inputs, it produces unique output. Arctangent 2 is part of any mathematical software library.
Okay, thank you. Now it's clear.
Yeah, no, I'm glad I could discuss something that is of immediate practical importance to all of us. Now back to more abstract Bode plots. So anyway, as I was saying, this is difficult, right? Lines, arctangents, im real, etc. Let's unpack a little bit. So what is this? Well, this is just a length. If you think of a complex variable as a vector on the 2 axes, real axis, imaginary axis, this is just a length of this vector. How do you compute the length of the vector? Well, Pythagorean theorem, right? Real part squared plus imaginary part squared square root. So I don't know if I need to write it here. I will try, but to be honest, I don't believe I will do a good job. So yeah, it's already started very badly. Let's just see one more attempt. No, it doesn't look like I will be able to write. All right, anyway, I will abandon this idea. So anyway, it's going to be, oh, wait a second, there is also an option like this. Can just take a real part plus imaginary part, and we take square root of this whole thing. All right, good. So this hopefully is clear. This we just discussed what it is, right? And you can see 2 inputs are vertical component and horizontal component. That's it. So that's how we compute amplitude and phase. But Bode plot is not that. It is amplitude logarithm in logarithmic scale. Notice we take logarithm and times 20. Who in the chat can tell me why 20? That is a famous fact that I think some of you may know without me telling you. Why 20? No? All right, let me explain. And that is basically why just one of those common knowledge, maybe useless, but kind of like things that you can throw around in conversations if you want, or be happy to know. I don't know. It's like just pleasing detail. Well, the reason for 20 is this decibel. Decibel, right? I think pretty much all of us know the word decibel. That's how we measure the volume of sound, right? But what actually decibel is like we can think about it as a sound, like volume of sound, or power of sound, whatever. We can also think about it in terms of amplification. But anyway, why 20? Well, deci is 1/10, right? Decimeter is 1/10 of a meter. I don't know if it is famous in English-speaking countries, but in Russian we, at least in school, learn what a decimeter is. It's 1/10, basically. So decibel would be 1/10 of a bell, and the bell was the name of a director of a lab that was testing, director or engineer, I don't remember, was testing this phone technology back in the day in America, and they wanted to name it after him. So it was bells, but it ended up being more useful to discuss decibels. And decibel would be 10, 1/10 of a bell. So obviously it would be 10 times more. There will be 10 times more decibels than bells. So 10 is from there. Why 2? Why 20? So, 20 is 2 times 10. So I explained to you why 10. Why 2? Well, what the lab did was working with energy. And energy is a square of, let's just say, amplification. Like you have a signal, and you want to find the energy of the signal, you square it. That sounds a little bit abstract, but you can think of velocity in mechanics. If you want to find its energy associated with velocity, you square it, right? Think about electrical systems. You would find that I think what would be the expression for, all right, let me not go into tangents in the territories where I'm not the expert. But anyway, energy is usually something squared, right? Signal squared. But when you take a log of a square, what happens is the 2 pops out, right? So that's where you get 2. So this completely random expression for decibels, 20 times log of a whatever, that is just thanks for this historical reason. There's absolutely no other reason for that. So deci in the name, they defined bell as a log, and that's a decibel. And if we wanted to work with energies, we would have had 10 here, but we work with signals. So anyway, and here is just degrees. That's all. I think this becomes very confusing when you look at it for the first time, but there is nothing confusing here. It's actually very, very simple. Okay, let's see. So next we'll have an example, but before we do, let's take a 5-minute break. And let me just look at my clock. It will be literally 5 minutes. So in 5 minutes I will start. Is that okay? And you can think about decibels in the meantime. All right, I'll pause the recording. Right, so now let me just show you how we can actually compute Bode plots on an example. So here's a very simple example. Let me just here's a very simple example for transfer function. This is a transfer function 1 over 1 plus s. We want to compute its Bode plot. Again, what we want is its amplitude in decibels and its phase in degrees. So first we substitute here instead of this instead of Laplace variable, this frequency domain complex variable. And that's what we get. This complex ratio. Obviously, if we want to compute its, I mean, we can plug it into a software and it will already compute something. But if we want to do it by hand, what we want is to make sure that complex numbers are not in what they call it, denominator, not downstairs in the fraction. We want them to be upstairs. How do we do it? Well, the simple trick is to multiply both by the same expression as in the downstairs, but with the opposite sign. So here we have 1 plus j omega. We multiply both sides by -1 minus j omega. And downstairs becomes 1 plus omega squared y plus, well, because the square of this is minus omega squared, right? J omega squared is equal to minus omega squared. because square of G is -1. And here you remember this formula, right? A plus B times A minus B is A squared minus B squared. Okay. What is this guy? This guy is just a two fractions. This is the real part. Like this whole thing is the real part. Right. And this whole thing is the imaginary part. So here you get the real part, 1/1 plus omega squared. And here is the imaginary part. Yeah. Sounds very simple. If we wanted to plot those, we are already done. That's what we have. But what we want to plot is actually not real and imaginary parts, but amplitude and in decibels, remember, and angle. So for the amplitude, what we do is we square this plus square this and square root of it. So that's how we get this expression. Square root of 1 y minus, basically. Is it a mistake? That is a mistake, right? It should be plus, I think. Correct me if I'm wrong. Wait. Amplitude of a complex number. Let me not make a mistake. But anyway, let's make a question mark here.
I think that W is real in here, right?
Oh, sorry. Sorry, 1 second. Could you even hear me? Could you even hear me before? I had the wrong headphones on me. Sorry.
No, it worked perfectly.
You could hear me, right?
Yes.
Yeah.
Okay. Sorry about that. I have 2 earphones and I put on the wrong ones. So what was the question? Was there a question?
I think that W is real, then it should be plus. Under the assumption that W is real, right?
My question basically is, let's verify that amplitude of a complex number. I think it should become computed as a plus, right? Yeah, because it should be plus. I think. All right, should be plus. Is just a typo. All right, now this is how you compute the. This is how you compute the angle. Obviously, you put it under logarithm, so it's there is like not a lot of problems there. Now, let's think about why we wanted to commit Bode. So far, we just we just found those plots not very interesting. Didn't give us any insight. So let's start to see how we can analyze it. So before we do that, let us remember that for a closed loop system, we had this expression. What is a closed loop system? Let me go to the whiteboard again, if I can. All right. So what is closed loop? Well, let's say we have this system G. Remember last time what we said is it has output. We want the output to be something, all right? The temperature in the tub, or the temperature, sorry, it's the kettle, it's the boiler. We want it to be a certain amount. What we do is we take this measurement of this temperature and feed it back here, where we subtracted from, let me try to draw it at least somewhat nicer. Where we try to subtract it from what comes on the input of the system. So let's say the input is 50, and here is 20. We subtracted, let's say 30. When here it becomes 40, we subtracted, we say 10. When here it becomes 50, we say 0. So point is, since it is linear system, it's going to how should I put it? It's going to yeah. I mean, my point is we want to arrive somewhere and stay there. Like usually what we want here is if we wanted like a 0 also output, it would actually make I think like the perfect sense. But anyway, what we have here is error, measurement of the error. It would error. It would make I think like perfect sense once we study it all in terms of linear, in terms of algebraic equations. Like next lecture, when I give you this feedback control in terms of state space, it will make perfect sense. Now in transfer functions, I do hand waving instead of explaining, and I'm not super happy about it. But basically, you saw this feedback loop last time, and where we wanted to subtract the output of the function from the input to make sure that as it reaches certain outputs, it stops, like it kind of winds down and shuts down, instead of just, for example, boiling water infinitely. All right, now what we saw is the transfer function of this guy is g of s plus 1 g of s. That was the transfer function of this guy, of the closed loop system. And if we had a controller here downstairs, if I had a controller here, the controller was h. The transfer function would have been g of s times 1 plus h s g of s. Remember, it's all scalars, so they are permutable. So what I'm trying to say is, if we have this type of structure, we know how the transfer function will look like. I'm not sure if this is convincing for most of you that this type of structure makes sense. It will become convincing next week, that I promise. And I think maybe pedagogically speaking, it would have been even better to first convince you that this is great and then teach you how to use it. But this is, I'll convince you that this makes sense next week. But we know how this looks like in terms of transfer function, and we know how this looks in terms of transfer function. And this is how it looks like. All right, let me go back to Bode. This will become relevant in just a second. So here is a case when we don't have a controller. It is g of s divided by 1 plus g of s. We can do the same substitution, frequency domain substitution. We get g of j omega divided by 1 of g omega. The same thing. Now, what we can see is that this function becomes ill-defined if this guy is equal to -1. That is a big problem here. If this guy is equal to -1, this transfer function will blow up. Does it make sense?
Yes.
So this is a way we are going to analyze it. What we are going to be scared of is g becoming -1. And we would want to avoid that. This is actually like the big idea around Bode plot, to see if g can become -1. Bode plot assumes you are going to use the feedback the way we draw on the whiteboard. So what it tells you is that what it allows you is to analyze how close you are to the situation when it blows up. Okay, so what does it mean for g to be -1? Well, the amplitude of this function would have to be equal to 1. The amplitude, right? And remember, we know what we draw the amplitude, right, on one of the plots. The amplitude will be equal to 1. So what is 1 on logarithmic scale? Do you remember? What is 1 on logarithmic scale?
0.
Yes, exactly. 1 on logarithmic scale is 0. That's exactly true. And phase of this function would have to be equal to 180 degrees or -180. That doesn't matter. Why 180? Well, think of complex plane. Here is phase 0. Here is phase 45 degrees. Here is a phase 90 degrees. Here is a phase 180 degrees. Right? You see, phase is just this distance, right? Like this angle, for example, for this complex number, here's phase. So for -1, the phase is 180. -1 is a complex number. It's just a complex imaginary part is 0. Does it make sense? Let's make sure that this last part made sense. I think the fact that here this guy would have to be -1 for it to blow up, that is clear, I think. The fact that g would have to be length 1 is also clear. I don't think any questions about that we'll have. But about the phase, I think that is maybe a little bit like different way of thinking.
Yeah.
But so anyway, like everyone understood it? Can I, you know, does it need some other explanation?
Yeah, because I didn't get how phase related to G.
All right. So let's go to the whiteboard one more time. All right. So G of omega j is a complex number. It has two components, alpha and j beta. It's just a complex number. That's the whole thing. Like this thing is just a scalar, is a complex number. All right. So what it has on the complex plane, it would have length, which is alpha squared plus beta squared square root, and angle phi, right? So the angle phi, so if alpha is equal to, is not 0, and beta is equal to 0, then this is the case. Let me then is the case here. And this means the phase is equal to 0. Makes sense, right?
Yep.
Now, if alpha is equal to 0 and beta is, let's say, is, let me write it by the way, like this. Instead of saying not equal to 0, I'll say positive. If alpha is equal to 0 and beta is positive, is here, that means the phase is equal to 90 degrees. Phase is again just this angle between this arrow and the horizontal line. Right? Does it make sense?
Yes.
All right. So the third case, alpha is negative, beta is equal to 0. This is the third case. You can see that the phi is equal to 180, right? All right, so that's how you can think about it. And -1 is exactly this case. Right? All right. So what we want to avoid is two things happening at the same time on the Bode plot. First, amplitude being equal to 1, which on the log scale means it would cross 0. Okay, that is one thing we want to avoid. Second thing is the phase crossing 180. But we want to avoid them happening at the same time. As long as they don't happen at the same time, we are safe. I hope you got me.
Excuse me.
Yes.
Could you please one slide back show? Thank you so much. You can continue.
Okay.
Sorry, sir.
Yeah.
Just 1 second. So here, when we consider the function g, we are just consider how to say, we are not interested in the actual function itself, but only by the fact that I'll say it gives a complex result, right? We're talking by amplitude and phase.
What do you mean we are not interested in the function itself?
I mean, when we are considering the how to say, the condition when g of j w is equal to -1.
Let's like g of s is a transfer function.
Yes.
We use its concrete value to determine to make a Bode plot. And on the Bode plot, we're going to pay extra attention to this condition that I discussed, -1 condition.
Exactly.
Mm-hmm.
But what I'm saying is when you consider the amplitude and the phase, we only care about the fact that this function is a complex value, not what the g is exactly as a function.
No, we care what g is exactly as a function.
Even when consider the condition that g is -1?
Yes.
Okay.
You will see it in a second. Let me show you the example of how we do a Bode plot. This is a third-party website. So they have a very nice Bode diagram. I wanted to make use of it. So let me just first let me make sure that I can annotate. Yep. All right. So here's a Bode plot. Here's this part of the plot is magnitude in decibels. You see decibels, right? Like we discussed that
Yes.
it is a log scale, but in decibels, right? And here's a phase in degrees. Okay, so what we care about is again 0 decibel line, like this line. That's what we care about. And here's when the plot crosses it. So this is a big point that we care about. This is a point where things can get ugly. And here on the phase diagram, we care about 180-degree line. And here are 2 points where things can get ugly. Right? All right. How did we get this line? Well, we got it from a transfer function. We got the transfer function of a, let me use G maybe. We got a transfer function of a system. We substituted J omega. Then we made the Bode plot. So this process requires the function itself. Like the last question was, do we actually care about the function? As in, is the structure of the function? Yes, otherwise we wouldn't be able to plot this blue line. Like the -1 argument cares about this horizontal line here, this horizontal line here. The function itself is responsible for the blue line, the plot itself. Right, so that is how it is. Now, the key concept in Bode plot analysis is margins, stability margins. What are stability margins? Well, let's look again on those 2 danger points. Well, what we can see is this plot can go down by 20 decibels, right? By 20 decibels, it can go down. And then if it goes down by 20 decibels, this point here will be here at 0, exactly when this plot crosses 180. So if this plot goes 20 decibels down, we would have -1. Like this would be 180, this is 0. So this is how far we are in terms of these points of danger from instability. Stability is probably not a great term here, but that's how much of margin we have here. Notice it has nothing to do with stability in terms of Lyapunov, or let me better say, it has nothing to do with stability in terms of eigenvalue analysis that we discussed before. This is rather an explosion in reaction to the input. If there was no input, none of this analysis would matter. Like this analysis is a frequency analysis. Like this horizontal line is about frequencies. So, you know, like this line here is some particular frequency, and at this particular frequency will become unstable if you want. You know, what will just behave badly. So, like, important not to mix eigenvalue analysis and this analysis. But we will discuss it a little bit more in a while. All right. So you saw this idea, right? If I shift this by 20 decibels down, bad things will happen. That is not the only possibility. Let me show another possibility. Let's look at this point of danger. We were looking before at this point of danger, right? Let's look at this one. If the phase of the system shifts up by, I don't know how much, 9 degrees, 9 degrees up, then again, bad things will happen. We would have -1, 180 here, 0 here. So traditionally, we discuss those shifts as margins. We can call them stability margins. We usually call this one gain margin and this one phase margin. Okay, is just what we call. What do I mean by shift? Like, does it make any sense? I mean, the Bode plot is what it is. It's not going to shift anywhere. Saying that what if it shifts is kind of like, you know, kind of like saying what if the Earth was closer to the sun, right? It's not very productive speculation. Well, let me remind you of what we saw just a little bit before. There was a chat. Let me see. As I understood, magnitude should be 1 to blow up. Why are we talking about 0? Okay, great. So 1 is on the normal scale, 0 on the logarithmic scale. Logarithm of 1 is 0. So 1 on the logarithmic scale is at 0, right? That is a very good question. Like Bode, at least half of the, like, you know, I would say a third of the difficulty is because we skip over a lot of math. Like we don't study Laplace properly, we don't study Fourier properly. That is difficult, right? Another third of the difficulty is decibels, those horizontal lines, G omega, G, like what is all of this is just a little bit difficult to grasp at a glance. And the rest is a legit difficulty. But you can see, you know, when you kind of pay attention, none of it is very difficult. Like, yeah, 0 is just 1 on different scale. But that is why we need a class on that. Why, you know, it's nicer to study it or in an organized manner. All right, so now let me go back to what I was trying to say. Why I'm talking about margins, why I'm talking about shifts. I remember previously I mentioned that we had this scenario where we had our plant J of S. Sorry about the horrible drawing. With this feedback loop. So the output of the plant was fed back into the input of the plant. All right. But we also considered this scenario where we had the output of the plant fed back to the input again. But there was a modifier, there was a controller, what we call it, the feedback loop. By the way, this notation here, when I have those black triangles in the downside, just means minus. Like, you know, traditionally this would mean plus, and this would mean minus. It's like algebra. Is notation that people in the know. I apologize for cryptic stuff. Control theory is like that. But anyway, it will become much clearer next week, I promise. But you remember this guy, right? For this guy, like for this, let me step back for a second. For this guy, the transfer function is this. For this guy, the transfer function is this. So let's say here we have just a gain. Let's say it is 10. So what we can have is this, right? Gain means amplification. Notice, please, that now in order for the system to blow up, we don't need -1. What we need is -1/10. Okay. So basically, when we say gain margins, what we say is how much we can amplify this function before everything blows up. This guy can also have a phase shift. Like it can be a function that shifts the phase, right? Like real number is, of course, phase is 0. But if it was like, if h of s, for example, was -10, its phase would be 180. And suddenly, in order to blow up, this would have to be not -1, but 1. So what I'm saying is, controller, this guy, can shift the phase and the amplitude, change the amplitude of this guy. And stability margins, let me just go back. So we can look one more time on our thing here. And those stability margins tell us how much we can allow the controller to change. So here what we say is, as long as the controller doesn't shift us by more than -20 decibels, we're okay. If it shifts us by +20, +40, no problem. -10, no problem. -20, big problems. What we say here is, as long as the controller does not shift us by more than -9 degrees, we're good. So notice we here have -135, -180, -225. Is just a matter of how you count. But okay, so -9 degrees. Big problems. If it shifts us by +9, no problem, and so on. So what I'm trying to say is, those margins, you can think about them as something that the controller can do to us without us blowing up. Let me try, it's going to be a little bit hard, but I will try my best. Let me try to demonstrate how it looks like when controller does something. So let's say the controller shifts us by -10 decibels. It'll probably be something like this. Like this. Like this. Like this. If it only shifted the decibels, that is what we will see, this new graph. Sounds good. We still are stable. All right. Here, if it shifts us by purely by phase, again, stuff will be good. What can actually happen though, is that it can shift us in both directions at the same time. And I would not, and then, you know, then you would have to wonder. Then you would have to wonder. Like, let me, all right, let me give you a very simple example here. Let's go back to what I just said before. What if G is close to -1? The question in the chat. What if G is close to -1? Wouldn't that be hard to control? Maybe I don't get the concept of control. No, it's a good question. The idea of what is hard to control, you will see again, you know, we'll have a rigorous discussion tomorrow. So let's just leave it at that. Today we're going to just wrap up with analysis in terms of transfer functions. Tomorrow we'll just get, you know, understanding of tomorrow. Sorry, next week, get a proper understanding of what control is, what is hard, etc., etc., etc. Okay, so I'm just not going to discuss the idea of control today because we are going to do it next week. Today, just margins. So let's look at this green line. That was just our controller, for example, shifting our gain somehow. Notice that this danger point that used to be here, that used to be here, no longer exists, but we have a new danger point here. Like this doesn't exist anymore. Now we have a new danger point. And that means that luckily for us, the phase margins are still the same. All right, now let's imagine the following. I'll draw the same thing again, but this time they are shifted up by 10 decibels or 20 decibels. Hard to draw exactly. I'll try my best. By some amount of decibels, they are shifted up. All right. Now this danger point again. Danger point, by the way, is just me using simple words. That's not how, like gain crossover. You see phase crossover frequency. That's what they call it. But I think I can allow myself one made up term. This danger point goes away, but we have a new one here. Looks innocent enough, right? Is innocent enough is just a shift by phase. But please notice that for this danger point, here downstairs, the frequency margin is completely different. What used to be -9 degrees margin became +20 or something. So the direction in which phase margin points changed. And that means, interestingly enough, that somewhere while we shifted, it went through 180. So what I'm trying to say is that Bode, you need to be careful about how you analyze those margins. Bode is actually a very primitive way of analyzing those things. People often advocate to use Nyquist, which is a different plot, but it is even more difficult to understand this than Bode. And Bode, while I'm saying it is simple, I know it is not easy to understand. But anyway, you can understand this idea of margins. Just notice that if you want to actually draw conclusions about how your controller will behave. Just plot the new Bode plot after the controller is applied, and see, see how the margins look after that. Don't just trust the original margins, because that can lead into trouble. By the way, shouldn't there be a minus before 180? Yeah, it should be. It's just the minus here is just gobbled up by this text, I think. There is a minus before 180. All right, so I think you somewhat understand the idea of a margin, right?
Yes.
Okay. Right. Let's see if I can. Give me a second. I'll try to go back to. All right. Now, last thing for today is we do have like 10 more minutes, right? I didn't check. Do we? I think.
No.
We don't?
Yeah.
All right, sorry about that. All right, then I'll just take like 2 minutes. I will just quickly show you and we'll go. All right, so here you can the lecture will be in the GitHub today, and you can and this is already on GitHub, so you can check it out already. So anyway, this is how you can do Bode. You'll practice during the practice session. Basically, you create a transfer function and you call Bode like this. It's extremely easy, and it gives you horizontal line, that is frequencies, magnitude, and phase. You plot it. Here is the idea. Notice that here the danger points for magnitude are somewhere never. Like it doesn't never crosses 0. It approaches 0 but never crosses it. So it would have infinite, like it would never have any problems with that. But the margins, might be small. Here again, never approaches minus 180. So this function is completely stable. All right, you can do it by hand. Here, I just define my transfer function. I define transfer function, real part, imaginary part. Just go over it, plot 20 log 10, use log 10, not natural logarithm. This whole thing are tangents 2, and we see exactly the same result. What I'm trying to say is that you don't have to just hope that some magical Bode from SciPy signals works. You can just do it by hand. It is very, very simple. But you would have to provide this stuff by yourself. So you have to derive it. This is from the lecture. All right, that is it. Alexander already asks me to give him the mic. So I will stop with that, and we'll see each other next week. I will stop this call, create it anew, and we'll go. All right, see you.